In this section, we're going to take a look at some of the most common index operations that Oracle uses. Generally, you want to prefer index operations, but not all index operations are created equal. Let's see what we mean by this. The most common index operation is an index range scan. You will see an index range scan used whenever Oracle is using a non-unique index to perform an index lookup operation. You will also see this operation used if you are accessing a range of data on a unique index, either by using the between keyword or greater than and less than operators to specify the range of the data in your where clause. The range scan in the name indicates that this operation can and most often will match multiple rows. For example, in this slide, querying the table using the last name of Nelson will result in multiple rows being returned. What this means is that this operation will return multiple row IDs, each one pointing to a row of data that matches the index lookup operation. To perform this operation, Oracle is going to traverse the B-tree structure of the index, working its way down to the leaf nodes at the bottom of the index. Inside of the leaf nodes, there will be the index key values, and for each index key, a row ID that points to the location where the corresponding data is found. Having the row IDs, Oracle can then use a table access by row ID operation to access the data it needs, and as we've just seen in the prior section, this is a very efficient operation. The data in the leaf nodes of the index, which are these nodes at the bottom of the index, is stored in sorted order. So once Oracle's at the leaf block level, it can traverse the index horizontally to scan for any data that it needs. If you think about an index on a date column, which is the example shown here, you might have a query which is specifying a date-time range. What Oracle will do is traverse the index vertically to find the leaf node with the first date in the range, and then scan through the leaf nodes sequentially until it finds the last date time in the date range. Index operations like this are very efficient, because this B-tree structure is usually only 3 or perhaps 4 nodes tall. In this way, Oracle only has to read a couple of blocks that contain these branch nodes at the top, and perform a couple of comparisons, and then Oracle's already at the leaf node level, where it can quickly scan through the data in order to find the rows of interest. Consequently, anytime you have a table of any size, you want to make sure that your SQL statement is using an index. By using an index, Oracle will only need to read a few blocks to find the appropriate keys in the index, and then read only the blocks it needs from the table, which again is a relatively small number. By using an index, Oracle is minimizing both the amount of data that it may need to read from disk and the amount of data it has to process. The result is a SQL statement that will execute very quickly in terms of response time and be very efficient in using system resources. If you have a unique index on your table and you specify the value that you need in your where clause, Oracle will perform an index unique scan. Once again, Oracle will traverse the B-tree structure of the index, but in this case, Oracle knows because the index is unique, it is only looking for a single index key and therefore a single row ID. Once Oracle locates this information, it can go ahead and perform a table access by row ID. If you ever query data in a table based on the primary key, this is the operation that Oracle will use, and this operation is why primary key queries are so fast. Traversing the index structure is typically only 3 or 4 I/O operations, and then there will be a single I/O operation to get the actual row data from the table. So Oracle is able to locate the row with a minimum amount of effort. Earlier in this module, we saw the term access predicate used with index operations in an execution plan. Whenever an index range scan or an index unique scan is used, you will have an access predicate associated with these operations. When Oracle is using an access predicate, it is using a condition in the where clause or a join condition in order to traverse the index and then only read the blocks it needs to. In situations where multiple rows could be returned, like a non-unique index or a where clause for a range of values, the access predicate also determines the start and stop points of what blocks Oracle has to read in the index. This is why an index operation is so surgical, because Oracle is reading and processing a minimum amount of information. Rather than the filtering of data going on after data has been read, the filter is being applied up front. This not only saves I/O operations, both logical and physical I/O, but also saves CPU, because Oracle has many fewer rows to examine. Index operations can also have filter predicates applied. Just like in table operations, filter predicates are applied after the data is read from the database object, in this case the index. Since filter predicates are applied after data is read, they do not reduce the amount of data that must be read for the operation. However, a filter predicate on an index operation will only apply to the data read in that index operation. So if an index operation contains both an access and a filter predicate, the access predicate will first be applied to only return a small subset of the index values that match the access predicate, and then the filter predicate will run only on this subset of values, not on every value in the index. The next operation to discuss is an index fast full scan operation. In this operation, Oracle is going to read the entire index, and is going to read the index in an unsorted order. What this means is that Oracle is not traversing the tree structure of the index, it's just reading all of the blocks of the index as fast as it can. And so in this sense, an index fast full scan operation is more closely related to a full table scan operation than to the index operations we've just looked at. What is happening is that Oracle has determined that it can get all the data it needs from the columns in the index, and it doesn't need to subsequently go and read more data from the table. In this way, Oracle is using the index as a type of lightweight version of the table. Since an index contains only a subset of the columns in the table, it will consume fewer blocks on disk than what the full table does. So Oracle is using that to its advantage in reading the index because this saves I/O operations over performing a full table scan. Like a full table scan, an index fast full scan can use multi-block reads to reduce the number of physical I/O operations that have to be performed for any blocks that are not already in the buffer pool. On the other hand, while an index will contain fewer blocks than a table, an index by itself can still be a rather large structure. And so while a fast full scan of an index is more efficient than performing a full table scan, it is much less efficient than an index range scan, as you are still potentially processing thousands or tens of thousands of blocks. The final index operation we are going to discuss is an index full scan operation. Note, this is different than the index operation we just discussed, an index fast full scan operation. In an index full scan operation, Oracle reads the entire contents of the index in sorted order. The typical reason for doing this is that there's an order by clause in the query, and every column in the order by clause is contained in the index, and the order of the columns in the order by clause matches the order of the columns in the index. A second scenario is that a query contains a group by clause, and that all of the columns in the group by clause are contained within the index. Since Oracle is reading the index in sorted order, it will use single block I/O operations to read any blocks from the disk that are not in the buffer pool. Consequently, this is going to be slower than an index fast full scan that uses multi-block I/O operations. This operation is going to be faster than a full table scan because, again, the index will only contain a few columns and therefore will be fewer blocks than reading the full table. Also, Oracle is getting the data back in sorted order, and so this saves Oracle from having to perform a sort once it has read the table. However, this operation is reading the entire index, and it's doing so using single block I/Os, so overall this is going to be a relatively slow operation.